As the second topic today, we'll focus on spatial clusters of rates or proportions. And first, we'll discuss what is special about rates, some important concepts, and then we'll deal with two particular ways of dealing with measuring local spatial autocorrelation for these proportions. One is based on an empirical Bayes logic, the EBI local Moran, and the other ones are the scan statistics. The scan statistics are by far the most commonly used cluster detection techniques in public health and crime analysis. Okay, what's so special about rates? The issue about a rate, a proportion, is that it's really a way to get at risk. So when you report the number of crimes, say the number of homicides per capita, what you're really trying to get at is what is the probability that you get murdered, in so many words, or you report the number of cancers of a particular type per capita. What you're really trying to get at, what is the chance, the probability that you get that particular cancer. And within a spatial context, rates are very important because they move you away from counts, which are spatially extensive, to rates which are spatially intensive. And let me get back to this a sec. So a count of an event, if you count the number of vehicles dropped in a neighborhood, abandoned in a neighborhood, the larger the neighborhood, everything else being the same, the more vehicles should be there. So counts can be misleading in that they only measure size. They don't really measure the intensity of the phenomenon. They only measure the intensity of the phenomenon after you convert them to something which is scaled properly, a rate or a density or an intensity. And Michael Goodchild makes a big deal about this in terms of choropleth maps, cartography, in that he argues that you should never make a choropleth map for spatially extensive variables such as counts, but you should always convert them into proportions, rates, densities, intensities, so-called spatially intensive variables before you map them. So the rate basically is a proportion, a ratio. In the numerator, there's the number of events. In the denominator, there's the population, and more technically, it's called the population at risk. So to be a proper proportion or rate and related to a measure of risk, the events have to come from the population. So that's why, for example, a density is not a proper rate, because the events, number of crimes per square mile, the population is not the square miles. The population is the people that could be criminalized or cars that could be burglarized and so on. So keep that in mind when you see variables that look like proportions, and they may be, but they're in that they are ratios, but that doesn't mean they're a proportion or a rate connected to a specific risk. And the reason that we make this connection to risk is that we're going to relate it to probabilities, and that will give us a handle to actually quantify the uncertainty associated with these measures. So the variable of interest is called a crude rate or a raw rate, and that's simply for a location I, the count of events, O of sub I, over the population at risk, P sub I. Now, many times in many disciplines, particularly in public health, instead of the crude rate, a relative rate is used. For example, standardized mortality rate. And what this relative rate does is it is a ratio of the observed number of events over the number of events we could have expected if some equal risk process was happening at hand. So, for example, if we have 10 homicides per 100,000 in the state at large, and in a particular county with a given population, you would want how many homicides you would expect given that 10 over 100,000. So you take 10 over 100,000 and you multiply it by the population of the county. That's what you would expect if the equal risk assumption, meaning every county has the same risk, holds. And then you compare that expected value to the actually observed value. And so if there's more cases in the county than you would expect, your relative rate will be larger than 1. If there's fewer, your relative rate will be less than 1. This is also the idea behind a standardized mortality rate. So if we look at the rates a little more closely, we see that the numerator, the number of events, is really the random variable. The population or population at risk in the denominator is just a constant, and that's not a random variable. So if we are interested in the properties of this ratio of two numbers, one of which is a random variable and one of which is a constant, first we focus on the random variable. And the number of events can be thought of as the realization of a binomial process. So it's a binomial variable. You can think of it as exactly the same process as the classic textbook example of an urn or a vat with red and white balls, and you just pull 10 balls out of the vat. How many are red? How many are white? So you any kind of draw, you count how many of the balls are a particular color. So you count how many events happen as a binomial process with a probability of pi. How many can you expect for a given population p? That would be pi times p. So the expected number of events is the probability of the event times the size of the sample, so to speak. In our case, the sample is the population. And then the variance, again using the properties of the binomial random variable, the variance is the probability pi times its complement, 1 minus pi, times the sample size or the population at risk. So right off the bat, we see that the variance is going to depend on the population. The variance of the number of events depends on the population. And the mean number of events also depends on the population. Now, moving from the numerator to the rate as a whole, p, the population, is just a constant. So the mean of the rate is the mean of the numerator divided by the constant. And so luckily in our case, this turns out to be very fortuitous. We have pi times p divided by p, so we end up with pi. So this crude rate or this raw rate or this proportion turns out to be an unbiased estimator of the risk, which is a good thing. The variance, however, we know if we have the variance of a random variable divided by a constant, we have to divide the variance by the square of that constant. So that is the result we had on the previous slide. Pi times 1 minus pi, the complement, times the sample size, p, divided by p squared. So now we see that the variance of the proportion, the variance of the crude rate, actually depends inversely on the size of the population. And there's a good intuition to this. The larger your population, the more precise your measure of risk is going to be. So, in other words, the smaller the variance. The smaller the population, the higher the variability, and which is the same as saying the higher the variance. So, if you try to measure, say, the risk of dying from a particular type of cancer, and you take a sample of 10 million people, and you measure how many have this cancer, and from that you estimate the risk of cancer. And you compare that with looking in a small village of 200 people and counting how many people have the cancer, and getting that ratio. When you have so few people to base your estimate of risk on, your variability, your variance, will be much higher. And the fact that the variance depends on the population, in a case of spatial analysis where the population varies across locations, then we have a problem. Because that means that the variance will be different at each location as well. And one of the fundamental assumptions for spatial autocorrelation analysis is that this variance has to be constant. So that's our problem. So the rates are actually different in two respects from a standard normal variable. First of all, the variance depends on the mean. The mean is pi. The variance in the numerator is roughly pi minus pi squared, and pi squared is going to be much smaller than pi, so in terms of orders of magnitude, this is determined by the risk. So higher risk means higher variance. Lower risk means lower variance. That is a mean variance dependency, which is exploited in, for example, generalized linear models. Then, more important from our perspective, is that the variance depends inversely on the population size. So smaller places will have a larger variance. And in particular, if the population at risk is very different from place to place, then the variance will be very different from place to place, which violates our assumption of stationarity. In other words, our assumption that the variance is constant. If all the places have a reasonable size, this is not going to matter very much. And that's why institutions like CDC, Centers for Disease Control, when they report risks or rates, they make sure that the size, the scale, the spatial scale at which they report it is such that the population is large enough that the effect on the variance is minimal. So, for example, you don't report anything unless the population is at least 200,000, because that's going to be have a minimal effect on the variance. But if you do what we call small area analysis, which is a big and growing field in public health, then you have to face this problem, because small areas will have very different populations, and therefore this instability needs to be taken into account. There's a large literature on how to do this. We don't really have the time to delve into it, particularly in terms of mapping and smoothing the rates for mapping. GeoDa has some functionality to deal with this, and just to give you an idea of how this matters and where this matters, on the top is a crude rate map of basically we have the number of schools per capita. So that's a probability of having a school, and we're interested in finding out if there's clusters of this. So we use our Nepal district example again, and on the top is your familiar box map, which has the two outliers located in the kind of the middle to the north of the country. And then after we apply a particular technique called empirical Bayes smoothing, so this shrinks the rates for districts with small populations towards the overall mean. When the districts have large populations, it basically doesn't do anything. So as a result of that, the areas with small populations will move towards the mean. So in the ranking, which is the basis for the box map, they may move out of the outlier category more into the mainstream, and some that were in the mainstream may now be bumped out into outliers because of the shrinking. The variance has been reduced. So these are the kind of changes that happen. Typically in practice, these changes are not dramatic. In our example, only one district is affected by this, and as I mentioned, it is an outlier that is no longer an outlier in the smooth map. So if you're interested, you can explore GeoDa, and there's a whole subset of smoothing methods to correct the crude rate for the variance instability and for the potential misleading impression of outliers or extreme values. In terms of spatial autocorrelation, the problem we have to deal with is this variance instability. As I mentioned, it violates a basic assumption underlying spatial autocorrelation measures, namely the stationarity assumption that the variance has to be constant throughout. With very different populations in particular in small area analysis, this is likely to be violated. How do we deal with it? Basically, two different approaches. One is to standardize the data and then compute the local indicators just the same way as we did before, for example, a local moran. And the other approach is the scan statistic approach. First, we deal with the local moran corrected for variance instability, or the EBI local moran.